Now this is modelling forced undamped vibrations. Initially A is at 0, given here, or A is at 0. In equilibrium, T of 0 equals mg, but T of 0 equals ke, so K of z equals mg. E is here, our extension from our equilibrium position, and the object is here. The top end of the spring is forced to vibrate, so that its displacement at t is given by this, y equals a sine omega t. Now if the natural length L of 0 and stiffness k on the object as mass m, then the equilibrium point A coincides with O. The object is at rest and the extension of the spring is E equals mg over k, which is given here at equilibrium position. There are two forces acting upon the object, gravity mg and tension. The acceleration is d squared x over dt squared. So applying Newton's second law, m multiplied by d squared x over dt squared equals mg minus t. The extension of the spring is t equals k e plus x minus y. The equation of the motion is therefore m d squared x at dt squared equals mg minus k e plus x minus y. So I expand the right hand side and recall that mg minus k equals 0. We get a more familiar form given here. Dividing by m and putting omega equals k of m, we get an even more familiar form here, or here, if we're talking about time dependency. Now if the system we have described is y equals f of t as a function of time, then it equals a sine omega t. This is forced harmonic motion, and omega over 2 pi is the forcing frequency. So the equation may be written as such. The complementary function is therefore a multiplied by sine omega t plus b multiplied by cosine omega t. And for a particular integral, we will try this form here, which seems a sensible choice. Then this will give dx by dt equals rho omega cosine omega t minus q omega sine omega t, and its derivative, the second derivative, is just minus rho omega squared sine omega t minus q omega squared cosine omega t. Now we substitute into the equation of motion, we get this, and we're equating coefficients and assuming omega does not equal, what are you talking about now? It is lowercase omega, I think it is. We get this for our values. So the particular integral is therefore given here. Well, the particular integral is here, which leads to this solution here for these omegas not being equal. But when they are equal, we get d squared x over dt squared plus omega squared x equals a omega squared sine omega t. So in this case, we try this with our time dependence, which seems like a sensible solution for this particular palaver. Now upon taking the derivative, we get this, and through lots of algebra the second derivative, and then we're substituting in, equating coefficients, and for cosine omega t, our p equals 0, and so our particular integral is here, a omega t over 2 cosine omega t. So our general solution is here. And this is our forcing term, and that's it for this particular short lecture. Please do like and subscribe. I've got lots more to come. I'm I'm going to do probably going to finish a series on classical mechanics and then go on a bit more extensively to general relativity and maybe some condensed matter theory or quantum field theory, or but I am planning on doing also a group theory and more pure mathematics kind of topics too. So please do like and subscribe.